Hello, everyone. My name is Oftano Gyargadze. I'm a solutions engineer here at Fortress Power. You can call me Geo. And today I want to talk to you about 208-120 three-phase with NV inverters. So how to accomplish that interconnection, what to pay attention to, and so forth. Essentially, we're going to be talking about different methods and key points when the NV inverters along with Fortress Power batteries are used in such application. Pay attention. I said 208, 120 volts, three phase. So we're not going to do 480 or any other type of three phase. Our NV can only support 208, 120. And speaking of 208, 120, as probably all of you know, there are two kinds really. There's Hilux Delta shown on the left side, which we cannot do. And there's Star or Y configuration, which we most certainly can do. Difference being that here you see the phases are in star configuration with the neutral in the middle. Here you have 240 with the neutral in the middle essentially, and then you have this so-called stinger leg. So with that in mind, let's get started. Let's start with a blank sheet of paper and slowly build up our way to the complete three-phase NV energy storage system with, in this case, I chose eVolt Max batteries for simplicity's sake. So let's get started. So first, as I said, we introduced the batteries. eVolt Maxes, number 1, number 2, and number 3. Again, we're using the minimum amount with 3 inverters. And first, we're going to discuss the case with 3 inverters. So that's why there are 3 batteries, not more or not less than that. Could have used more, but for our purposes right now, 3 will suffice. Then, as I said, 3 inverters, NV1, NV2, and NV3. So how do we interconnect these? One could say, well, connect first battery to the first inverter, second battery to the second inverter, third to battery to the third inverter, and voila. No, you cannot do that. You could do that with a split phase application, but with a three-phase application, that is not allowed at all, ever. Because, for example, if you were doing this with a split phase application, what would happen is that if you were to lose one of the batteries for whatever reason, um, you would just lose some power and some capacity. Here, you might actually lose a phase. We don't find that being acceptable. That's why you are required to use a bus bar or 2 bus bars, one positive, one negative, between the inverters and between the batteries, so that all inverters use the same combined battery bank consisting of multiple Fortress Power batteries. So, as I said, 2 bus bars, positive right here. Let me see if I can get a highlighter very quickly to make it a little more visible. Okay. So positive bus bar over here and negative bus bar over here. Small legend here so we can read the diagram better. But again, 3 inverters, 3 batteries, bus bar in the middle, 1 positive, 1 negative. Obviously, you are going to need to choose the right bus bars so that the bus bars can support the ampacity of the inverters. We are choosing here 1000 amp bus bars. Both of them are rated at 1000 amp bus bars or 1000 amps. And here's the reason why. There are 3 inverters. Each of the inverters can output 250 amps of DC current to the battery bank, or they can extract 250 amps from the batteries. So all 3 combined deliver 750 amps or extract 750 amps from the batteries. Combined input or output current is 750 amps, but that 750 must be at least 80% of the bus bar's ampacity rating. So we divide 700 amps by 0.8, or you could also, instead of division by 0.8, you could do multiplication by 1.25 shown here, and you get 937.5 amps. This is the minimum ampacity that this bus bar would require. I don't believe you can find something this specific. So the closest rating that is commonly available on the market is 1000 amps, and that's why we're using 1000 amps. Next, we are joining the positives of the batteries to the positive bus bar. and we are doing negatives of the batteries to the negative bus bar. We're doing the same for the inverters, right? Positive ports of the batteries connect to the positive bus bar, and the negative ports connect to the negative bus bar. This is very important. One thing is choosing the right ampacity bus bar. Also, you need to really keep in mind how many ports or studs you need on that bus bar. Minimum quantity of terminals or ports on each bus bar must be no less than the total quantity of the inverters and the batteries. So essentially what this says is that you have 3 inverters, you have 3 batteries, so this bus bar must have at least 6 ports, 3 for 3 batteries and 3 for 3 inverters. If you were to get a bus bar with 5 ports, well, you would either not be able to connect one of the batteries or one of the inverters. And that will be very frustrating if you're encountering that in the field. So, again, pay attention to the ampacity, do the calculation that I showed, and also make sure that the ports on the bus bars are enough for your equipment. You see also here that we have connected the inverters and the batteries to these bus bars, but it is also very important to keep in mind that when you're using cables for such connection, you do it in a way that for each battery, you have identical pairs of cables. So types of cables must be the same, and length of the cables they use for the first battery, the same length you should use for the second and the third. And same applies to the inverters, so that the charge travels the identical current from all batteries, or from each battery to each inverter, or from each inverter to each bus bar. So if you don't follow this rule, and let's say if you have super long cables for the first NV inverter and very short cables for NV2 inverter, and again, super long cable for the third, what will happen is that the distribution of output current will be uneven, or input current will be uneven to the inverters. That's more or less okay. But if you do the same thing with the batteries, one of the batteries will be constantly at a different cell voltage level than the others, and that is completely unacceptable. So you do your best so that the path traveled from each battery to each inverter is uh, identical for any pair of batteries and inverters. So again, inverter to busbar cable pairs must be identical for each inverter, and battery busbar cable pairs must be identical for each battery. Okay, so since we're clear on that, now let's talk communication. So we connect the communication between the batteries as the battery manual suggests. So for example, we have eVolt Maxes here. You have 2 ports. Most of the time you will have 2 ports actually. The same for E4, same for eFlex Max. So essentially you daisy chain the communication cables, or with communication cables, you daisy chain the batteries, right? And you need to decide which one in this case is the primary battery. Let's say in our case, it's eVolt Max 1. The primary battery then connects to the primary inverter with the communication cable. So communication from the primary inverter to primary battery, and then all batteries talk to each other because they're daisy chained together with the communication cables. Well, let's see what it reads here in bold red. Inverter to inverter communication is not shown, but is assumed because it must be connected at all times. Could not be clearer. You must connect the inverter to inverter communication every time you use multiple inverters. And also, I'm going to quickly make a quick note. When multiple inverters are used, those inverters must be powering the same set of loads or panel, um, because if they try to cover different panels, let's say we have one panel for NV1 and two, then one more panel that is powered by NV2 and NV3, your system is going to go crazy because they try to balance the output between each other. But if loads are different, or load demands are different on each inverter, the inverters will throw a bunch of errors and stop outputting any power altogether. So again, one group of loads. So essentially, it should be powering one panel on the load side, the entire system. We're going to get to that later. But before you power anything on the load side, you might need to split the grid input between the three inverters, and that's where the grid splitter panel comes into play. So grid splitter panel allows for grid to inverter connection via the breakers in it, shown right here, 3 of them. Thus, splitting the grid between the inverters has the name. Grid splitter panel is a mandatory item. Small caveat here, it is a mandatory item if it's a grid-tied application. If it's off-grid, obviously you cannot have it and you will not have it. But other than that, yeah, we have just introduced the grid splitter panel, and the entire function of it is to split the grid input to smaller sub-inputs to each inverter. Let's see how that is done. So first breaker, we see L1 and L2. We connect to L1 and L2. Second one is L1, oh, I'm sorry, L2 and L3, and they connect to L1 and L2 ports on the second inverter, right? And then, let me hide this thing. We have L1 and L3. We use the ports L1 and L2 of the third inverter. This is the way to do it. You cannot have two L2s here and two L1s here and two L3s here. The way I'm showing it here, this is the way it is shown in the manual. You're going to follow this color code and you will have no problems whatsoever due to the grid interconnection, right? So again, L1 and L2 of the first inverter is for line 1 and line 2. L1 and L2 on the second inverter is for line 2 and line 3. And L1 and L2 on the third inverter is for line 1 and line 3. And these are not reversible. You cannot have L3, the blue one, connected to L1 and black one, L1, connected to L2. It has to be the way I'm showing it right here. Then, so we have split the grid between the inverters. So now the inverters are interconnected to the grid. Well, almost, but we'll see that later. Now you need to combine the output of the loads, and you introduce the load combiner panel. Allows for combining the output of the inverters to power the loads. Load combiner panel is a mandatory item. It is a mandatory item because, as I said before, all 3 of these must be covering the same loads, right? So you have the load combiner. So essentially, whatever loads the output of this panel is sent to is essentially all 3 inverters are powering whatever this panel powers, because this panel just combines the output of the inverters. And again, this is a mandatory item. You must always have it. You follow the same technique as for grid splitter. So L1 and L2 connect to the NV1s, L1 and L2. L2 and L3 connect to the L1 and L2 of the second inverter. And L1 and L3, again, connect to L1 and L2 respectively in the third inverter. So you see the color code is identical. And L1 and L2 connections are also identical in terms of sequence. What changes is that here you had grid splitter and you were connected grid here. And here you have load output of the inverter going to the load combiner pan, right? So next, let's introduce the generator to all of this. Generator splitter panel is very much similar to the grid splitter panel. It essentially is that, provides the same functionality and does the same thing what the grid splitter does for the grid. So essentially the bus bars inside this generator splitter are energized by the generator. And then the panel with these breakers splits that generator input into smaller inputs to each inverter. I use the dashed lines so that you could easily distinguish this from the splitter or from the load and grid cables. So let's see what it reads here. Allows for generator inverter connection via the breakers in it, thus splitting the generator output between the inverters. Hence the name generator splitter panel is a mandatory item. Again, it is a mandatory item when there is a generator present. If you had AC coupled PV, for example, instead, you would use the same panel. It's just instead of a generator, you would connect the AC coupled PV inputs here. So generator is connected to the generator splitter, but also our inverters, they have auto start or two-wire start functionality by default. So you can connect two-wire start to the inverters, but you always go for the primary inverter, which would be NV1, as we have established before. So communications from the battery bank and the two-wire start wires come to the NV1. And essentially, then you program your inverter, telling it at what battery percentage the generator must turn on and at what battery percentage the generator must turn off. Obviously, the latter being greater than the start percentage. Now, you can do it different ways. You can have whole home, but this will not be a home. So you could do full backup, or you could do partial backup. The difference being that when you're doing full backup, there is nothing upstream of the inverters. So there's meter, then there's generator splitter, and no loads whatsoever. When you're doing partial backup, what happens is that you have some loads upstream of the inverter and then backed up loads downstream of the inverter, right? We introduced panel F right here, which is a backed up panel. So if you're doing full backup, this will be your main electrical panel or main distribution panel, as sometimes they call it. You also can add one more thing. So you can add manual transfer switch so that you have a possibility of bypassing the entire energy storage system with the grid so that the grid is able to deliver power directly to your loads without it going through the inverters. Because essentially from here, this is already a full setup, right? You have your meter and the grid is connecting to the splitter panel, and the splitter panel connects to each inverter, and then you have the load panel connected to the load combiner. So what happens is that your grid power travels through this panel, all of the three inverters, then all the output of these inverters are recombined in the load combiner, and they power the main distribution panel. But if it was to if it so happened that you lost one of the inverters or you need some kind of maintenance, you would need to disable the inverters, right? And in that case, the pass-through is also disabled. If there is no pass-through, even if the grid is available, you cannot provide power to the main service or main distribution panel. That's when the manual transfer switch comes into play. So this allows you to bypass the energy storage system and provide power directly from the grid to the loads. So the grid comes in, and part of it goes to the grid splitter, and part of it goes to the manual transfer switch. You could use like Polaris here or whatever your HJ finds acceptable to split the meter output into the grid combiner and the manual transfer switch. So in this position, as we see here, yes, there's voltage applied to this point, but there's no continuity from this point to anywhere downstream. So power is not going to flow there. But on the other hand, you also have voltage applied on the grid splitter panel, which means the voltage is applied on the grid ports of the NV inverters, which means that there's a pass-through to the load. And if there is pass-through to the load combiner panel is energized. If the load combiner panel is energized, you have load combiner panel connected to the transfer switch, and the transfer switch has also the main distribution panel connected to it. So essentially, you have two inputs, one load combiner or one grid, and you choose between them. In this position, obviously, the power will flow through the inverters, through the grid splitters, through the load combiner. It will flow to the um, load port on the manual transfer switch, and then from there to the main distribution panel itself, right? But if I was to change the position of the manual transfer switch, then the power will not flow through the inverters. Because yes, obviously the grid will be applied to the grid ports of the inverter. And yes, the power can travel through load ports, but where is it going to travel to? Because it has nowhere to go. So there's no continuity after the load combiner panel. So yes, there will be voltage, but there will be no power flow. Whereas here, there is power flow, right? I hope that this is clear. Manual also shows this. So let's bring it back to default, and let's add one more item. That will be AC disconnect switch. Remember when I said that, yes, I changed the manual transfer switch position, and you can still have voltage on the grid ports, and you can have voltage on the load ports, and you will have voltage in the load combiner. Well, here, if I was to do this, at least the grid would not be able to provide voltage to the combiner panel. So if I have batteries and everything else disabled, if I was to turn this thing off, then the voltage will be lost in the splitter panel, on the ports of the loading grid, and inside the load combiner panel. If the grid is available and also the batteries and PV are available, what this switch is going to do, it's going to separate the energy storage system from the grid, which is great. Sometimes that's needed, sometimes not sometimes, but most of the time, the HA requires something like this. Especially, it needs to be visible and lockable. Also, you could put fuses in your disconnect, and you will have overcurrent protection too. So there's that. Now, there's one more type of application that we could cover. Is this is the most budget-friendly application, so to speak. You can use two inverters to cover 28123 phase, but with a certain limitation, which we'll discover in a moment. So you will notice that this is very much similar to the three-phase on the battery side. You still have the bus bars. You still have the communication, as we discussed you would have. You still have the generator to wire start. You still have the grid splitter. You have still load combiner and generator splitter. You have your AC disconnect. You have your manual transfer switch. And obviously, you have your main distribution panel. But notice what is different here. Before we had L1 and L2, and then we had on the second inverter L2 and L3, and then on the third inverter we had L1 and L3. Here it's a different story. We have L1 and L2, and then we have L3 and L1. You will notice that L2 connects here, L3 connects here, but L1 is present both in the NV2 and NV1 inverters. This creates some kind of a limitation. It changes the ratio of outputs. So previously, for example, if you had three 12K inverters, you would have 12 kilowatts per line. Here, because you have essentially two L1s right here, and L2 and an L3, the ratio of pass-through and current and power output will be altered. So you have two L1s, you have L2 and L3, right? So this means that if, for example, each inverter has 200 amp pass-through, right? On L1, you would have 400 amps. On L2, you would have 200. And on L3, you would also have 200. Let's say you have, I don't know, two 12K inverters, and combined, they can output 10.8 kilowatts per inverter. So combined, they can do 22.8. But what will happen is that it will be able to output twice as much power on the L1 than it will be able to do so on the L3. So let me do a quick calculation. 10.8 times 2. It's 21.6. Divide that by 3. So it would be 7.2 kilowatts for L2, 7.2 kilowatts for L3, and 14.4 kilowatts to L1, right? So that creates a difference. So if you need to have a balanced system, especially if you're going to be doing power export to the grid and so forth, we strongly recommend having 3 inverters or inverters in the quantity of multiples of 3, right? Speaking of multiples of the 3, we discussed here 3 inverter case, but you could also have 6 inverters, you could have 9 inverters, you could have 12 inverters. The only thing really that changes is that you right now have L1 and L2 connection to the first inverter. If you were to have 6 inverters, you would have L1 and L2 on the first inverter, and then L1 and L2 on the second inverter as well. So the second inverter would be mirroring the first on the AC side, obviously. The fourth inverter would mirror the third, and the sixth one would mirror the fifth. Bus bars obviously would need to be changed because you have now 6 inverters, right? So 6 times 250 divided by 0.8, that's how much capacity it should be able to handle. The battery sizing, 3 evolt maxes would not be enough because you need to have at least 1 evolt max per 1 NV through 12, for example. Our minimum sizing standards are given on our website, but please always pay attention to that. Otherwise, you could void your warranty. So, for example, if you have, I don't know, 5 eFlex Max batteries with NV through 12, 3 of them, that is not acceptable because you need to have at least 3 per inverter. So that would mean if you have 3 inverters, you need 3 times 3 eFlex Maxes, and that will be 9. If you go for 8, 7, 6, 5, or 4, or whatever, the warranty could be voided. The only reason why I say could be voided is because the sizing standards can be violated somewhat if you are not connecting anything on the load port of the inverter. So if you have just PV, you have your battery, and you have your grid ports connected to grid splitter, but there's nothing on the load side, meaning that when the grid is unavailable, nothing will demand power from the inverters and the batteries. It's just when the grid is available, you export the power, you can do arbitrage, you can do many interesting things, but you will not be backing up any load. There will be no pass-through. If that's the case, you can violate the sizing standard. We allow for that, but again, within the reason. But that's a unique case, so please do contact your regional sales manager, and then they're going to set up a meeting with someone technical, and you can discuss the project with them. But yeah, I just wanted to really give you the principles and good practices of interconnecting our equipment with our batteries and with the 3-phase 208 120 star configuration service. I think we have covered at least most of it. But if there are any questions, I will be happy to answer them. Let me see. Let me see if we have any questions. I'm going to stop sharing the screen and see what the questions are. Okay. Q&A. Okay. We have a question here. I have an outdoor application and will have to use eFlex Max batteries. In that case, does this same concept apply for each 5 kilowatt hour battery, or can they be stacked before connecting to the bus bars? So this is a very good question. Essentially, what this person is asking is, if I have 5 kilowatt hour or 5.4 kilowatt hour eFlex Max batteries, and I have the inverters, can I connect them to each other and then to bus bar? Or does each battery have to go to the bus bar individually? Busbar will still be needed, as this person is correctly determining, because you still have multiple inverters, right? Ideally, what I would prefer is having each battery connected to the bus bar separately. But since you are talking about eFlex Max batteries, the way they interconnect to each other is essentially you create the bus bar with those included conductors that go on the top. So what you could do is you could have symmetrical system. Let's say you have 6 batteries, or let's say you have, I don't know, 9 batteries. You could have string of 3, 3 of them, and each string would connect to the bus bar as if it was a separate battery. So string of 3, connect to the bus bar, string of 3, connect to the bus bar. Same for the third string. So you have 3 strings, i.e. 9 batteries connected to this bus bar, and now we can have 3 NV12s connected to it as well. I hope this answers your question. Strictly speaking, you could have string of 3 and string of 2, but it's always easier on the BMS to have identical strings. But yes, because this is a parallel connection with a bus bar, you can have shorter strings. Or uneven strings, should I say. We have a response. Okay, that's what I was thinking. Thanks. One more question about the minimum sizing. Yeah. So minimum sizing. Here's how it goes. I'm going to just verbally say it, and you can either write it down, memorize it. But as I said before, you can find that on our website as well. NV8K and NV10K, each of them must have at least 2 eFlex Maxes, at least 1 eForce, or 1 2-stack of eForce. That will be 2 eForce modules, or 1 eVolt Max. Again, 8K or 10K, minimum 3 eFlex Maxes, 1 eVolt Max. Let's start from the beginning. I'm sorry, I was reading something. For 8K and 10K, 2 eFlex Maxes, 2 eFlex Maxes minimum, 1 eForce module, or 1 eVolt Max. For 12K, at least 3 eFlex Maxes per inverter, at least 2 eForce modules, or at least 1 eVolt Max. That's the minimum for NV212. I see a question here. Did you say 3 eFlex batteries per inverter? 3 eFlex batteries per NV12 inverter. 8K and 10K can have 2. Got it? Thanks. Okay, cool. So this question is answered. If you have other questions, please ask away. I'm looking forward to them. It's a complicated matter. I don't believe I covered all 100% of it. I think it's impossible to do it without questions to guide me in the right way. So please ask the questions. Okay, here's a question. Can the 12K have just one 19.2 eForce? Yes. Yes, because 19.2 eForce, that has 2 modules, 9.6 each. You multiply that by 2 because you have 2 of them, and that's how you get 19.2. So yes, that is actually the minimum of eForces per 12K. All right, 2 eForce modules per 12K inverter, and 2 eForce modules happen to have 19.2 kilowatt hours of storage. So yeah, absolutely. Any other questions? Okay, I'm going to wait for 1 more minute for a new question to come in. If I don't see the questions, that's going to be the end of this webinar. And if you think of any other questions later, you can always contact our sales line, our tech support line. One of the bigger distinguishing factors about our company is that you can actually call us and someone will answer. And if someone cannot answer, we're going to call you back. That's very important and quite rare, in my opinion.
I was able to talk to one of your guys and then have to buy.
Okay. It seems like no one else has any other questions. That's fine. Again, if you think of any, let us know, and we're going to be happy to find you the answers or give you the answers right away. Most of the time, that's the case. Also, either this recording or maybe a slightly improved recording, we're going to make available for the public. And yeah, we're going to make it available on our YouTube or training portal, but this information will not be lost. You will have the access to it. So if later down the road you're going to need a refresher, you want to take a look at the diagrams one more time, you will have the access to the video. It's going to be public. But also, if you want to have the concept in front of you in the field or something, you're wiring something up and you're not so sure, please always refer to the manual. Manual has the not identical diagram, but it shows the same concept using the same method. So feel free to refer to that diagram or those diagrams and manual generally. With that, I do thank you for attention today. Thank you
Sorry,
all for
real quick,
coming.
Gio.
Sure.
There are 3 questions that did just populate at the bottom of the chat. I'm not sure if you can see them. Yeah,
Mm. Okay, I can see them. Very good.
Cool.
Very well. Thank you, Anthony. See, that's why we have a moderator. Let's see what the questions are. The project will be 6 inverters. Is it correct that we would need a minimum of 9 batteries then? Depends on the inverters. I don't quite understand how you get to the number 9 here though. You have 6 inverters. Let's suppose those are the smallest inverters that we have. That will be 8Ks. You would need at least 12 eFlex Maxes, right? Or at least 6 eForces, or at least 6 eVolt Maxes. Let's say it's the biggest inverter. If you have 6 inverters, you will need 18 eFlex Maxes, 12 eForces, or 6 eVolt Maxes. So 9 is not the correct answer in any of these cases. Will this configuration, next question. Will this configuration face any challenges with IEEE or IEEE interconnection compliance? No, because our inverters are IEEE certified, and we have that standard built into the inverter. So the limits of voltages and frequencies. So yeah, you can see that on the spec sheet. We've never had any negative experience with interconnection compliance with the three phase. Next question. If 3 of the inverters had no loads connected, only grid. Oh, I see. So I believe what's happening here is that I answered the question about this project will be 6 inverters. Is it correct that we would need a minimum of 9 batteries then? And I answered, and I think this person then clarified if 3 of the inverters had no loads connected, only grid. So if it was to be 6 batteries with no, or I'm sorry, 6 inverters with no loads connected to them, you could go as small as 9 batteries. Yes, absolutely, because the sizing standard, as I said before, is not that relevant. Yeah. So I'm sorry. I think I'm misunderstanding here. So first question was, this project will be 6 inverters. Is it correct that we would need a minimum of 9 batteries then? And then the follow-up was, if 3 of the inverters had no loads connected, only grid. If I'm guessing correctly here, if you're saying that you're going to have 6 inverters, they're going to communicate, and 3 of them will have no loads, and 3 of them will have some loads. As I said before, that's unacceptable. All inverters, either they have the same panel that they support, or none of them have any loads whatsoever. It's either or. It's not like 2 inverters can have loads and other 4 can get away without having loads. No, either you design the system with all the inverters backing up the same main distribution panel, or you design systems so that the inverters don't back up anything. If they don't back up anything, which means none of them back up any loads whatsoever, then only you get to violate those standards. And again, within the reason. You cannot have one 5.4 kilowatt hour battery and 9 NV12 inverters. If I'm making sense, that is really the approach. Yeah, so you got it. Thank you. Okay, yeah, okay. I was worrying. I was like, maybe I'm misunderstanding the question. Okay, good. As long as I have provided the answer. Cool. Any other questions? No, nothing. Okay. All I have left to do is just thank you all for attention. Again, what I said before is still true. We will make either this or even better recording, maybe the one that also covers these questions or provides answers during the recording to these questions. Maybe that we will make available to the public. Most likely it will be our YouTube channel, but also I don't exclude the possibility of having the video on our YouTube channel and the training portal. In any case, if you need to refer to it, you will have the video material to refer to. Again, don't forget to use the manual. Please remember that the manual has this concept outlined in it. And if you have any further questions or you have a very complicated project and you need some assistance with understanding what the limits of our equipment is and so forth, feel free to contact us either on tech support line or preferably on the sales line. So yeah, with that, I thank you one more time. Wish you best of luck with your future projects. We appreciate your time, your attention. And yeah, see you at the next time. Bye.